On December 14, 1900, a German physicist stood before his colleagues and presented a mathematical formula he would later describe as an act of desperation. Max Planck had not set out to revolutionize physics. He was trying to solve an embarrassing technical problem, a stubborn mismatch between theory and experiment that had been quietly haunting laboratories across Europe. The problem involved something seemingly mundane, the glow of heated objects. But hidden inside that glow was a contradiction so profound that it threatened the entire edifice of classical physics. Planck's solution, delivered almost apologetically that winter evening to the German Physical Society, introduced an idea so strange that even he didn't believe it was real. He thought it was a mathematical trick, a convenient fiction that happened to make the numbers work. What Planck had actually done, though he wouldn't fully grasp it for years, was crack open a door to a reality that operates by rules Newton never imagined. Energy, he proposed, doesn't flow continuously like water. It comes in discrete packets, quanta, indivisible units that you cannot split or subdivide. It was an idea that made no intuitive sense, violated centuries of accumulated physical understanding, and turned out to be absolutely, irrefutably true. That moment marked the boundary. On one side, classical physics, deterministic and continuous, where everything flowed smoothly and predictably. On the other, quantum mechanics, a universe of discontinuity, uncertainty, and behavior so counterintuitive that it still challenges our conception of what reality actually is. Classical physics, by the end of the 19th century, seemed nearly complete. Newton's mechanics described motion. Maxwell's equations unified electricity and magnetism. Thermodynamics governed heat and energy. The universe appeared to be a vast clockwork, operating by comprehensible deterministic laws. In 1900, Lord Kelvin gave a lecture titled 19th Century Clouds over the dynamical theory of heat and light. He suggested that physics had reached a state of near perfection, troubled only by a few minor anomalies. One of those clouds hung over blackbody radiation. A blackbody is a theoretical object that perfectly absorbs all radiation and, when heated, emits radiation across a spectrum of wavelengths depending solely on its temperature. In practice, scientists approximated this using a cavity with a small hole. Radiation entering would be trapped and absorbed, and the hole itself would emit radiation characteristic of the cavity's temperature. This wasn't abstract theory. Industrial Germany needed accurate models of thermal radiation to improve furnace efficiency and develop better lighting. Measurements were being made with precision at the Physikalische Technische Reichsanstalt in Berlin, the Center for Infrared Radiation Studies at the time. But there was a problem. Classical physics predicted something that experiments flatly contradicted. According to classical electromagnetic theory, a heated cavity contains countless possible vibration modes, standing waves of electromagnetic radiation bouncing between the walls. The equipartition theorem, a bedrock principle of thermodynamics, stated that energy should be distributed equally among all available modes. The number of possible high-frequency modes, short wavelengths in the ultraviolet range and beyond, is essentially infinite. If each mode received an equal share of energy, as classical physics demanded, then the total energy radiated at high frequencies should be infinite. A blackbody, by this reasoning, would emit unlimited energy, glowing with impossible intensity in the ultraviolet. The prediction was absurd. It violated the conservation of energy. It contradicted every measurement ever made. The term for this failure wouldn't be coined until 1911, when Austrian physicist Paul Ehrenfest called it the ultraviolet catastrophe. Two classical laws attempted to describe blackbody radiation. Wien's law worked well at short wavelengths and high frequencies, but failed at the longer end. The Rayleigh-Jeans law, derived from first principles of classical physics, worked acceptably at long wavelengths, but predicted that intensity would increase without limit as wavelength decreased, rising toward infinity as you moved into the ultraviolet. Reality, measured carefully in Berlin laboratories, showed something entirely different. A smooth curve that rose to a peak at a wavelength determined by temperature, then fell off gracefully at shorter wavelengths. No catastrophe, no infinite energy, just a curve that classical physics could not explain. Max Planck was a conservative physicist, deeply respectful of classical tradition. Born in 1858, he was by nature cautious, skeptical of speculation, methodical in his approach. As Max Born would later write, Planck had nothing of the revolutionary in him. Yet his belief in logical reasoning from experimental facts was so strong that when the data demanded it, he would follow the mathematics wherever it led. Planck had been working on blackbody radiation for years, trying to derive a formula that matched the experimental curves across all wavelengths. On October 19, 1900, he presented an equation to the German Physical Society that worked, a formula that elegantly described the entire spectrum. But it was empirical, a mathematical fit to the data. Planck didn't yet have a theoretical justification for why it worked. Over the following weeks, he searched for a physical foundation. Inspiration came from the statistical work of Ludwig Boltzmann, who had described entropy in terms of the arrangement of discrete particles. Planck applied a similar approach to electromagnetic energy, but with a crucial twist. He divided the total energy into finite portions, what he called energy elements, each proportional to the frequency of radiation. Energy, in his formulation, equaled an integer multiple of frequency times a new constant. That constant, measured by fitting theory to experiment, turned out to be approximately 6.626 times 10 to the negative 34 joule-seconds. It is now called Planck's constant, one of the most precisely measured quantities in science. On December 14, 1900, Planck presented his derivation to the German Physical Society. Energy, he proposed, is quantized. It cannot be divided infinitely. It comes in discrete, indivisible packets. Each quantum carries energy equal to Planck's constant, multiplied by the radiation's frequency. This single assumption resolved the ultraviolet catastrophe. At high frequencies, each quantum carries substantial energy. Thermal energy at a given temperature can't easily supply enough to create high-frequency quanta, naturally suppressing ultraviolet emission and eliminating the catastrophic runaway to infinite energy. At low frequencies, where each quantum is small, energy flow appears nearly continuous, matching classical predictions. Planck's formula described the blackbody spectrum perfectly across all wavelengths and all temperatures. The physics community appreciated the mathematical elegance. The formula worked, but almost no one, including Planck himself, believed that energy quantization represented physical reality. It seemed like a useful mathematical device, nothing more. Planck spent years trying to reconcile his quantum hypothesis with classical physics. In his own words, "My unavailing attempts to somehow reintegrate the action quantum into classical theory extended over several years and caused me much trouble." He would later admit, in a letter written in 1931, that introducing energy quanta had been a purely formal assumption, and I really did not give it much thought, except that, no matter what the cost, I must bring about a positive result. Yet, on the evening of December 14, 1900, Planck told his son Erwin that he had just made a discovery as important as Newton's. Some part of him understood. 5 years later, a patent clerk in Switzerland took Planck's idea seriously. In March 1905, Albert Einstein published a paper in Annalen der Physik titled "On a Heuristic Point of View Concerning the Production and Transformation of Light." It was one of 4 extraordinary papers Einstein published that year, his Annus Mirabilis, but this one would eventually earn him the Nobel Prize. Einstein's fascination with the hidden workings of nature began early. At age 4 or 5, he had been captivated by a magnetic compass, transfixed by the invisible force that caused the needle to point north. It convinced him, he later said, that there had to be something behind things, something deeply hidden. In 1905, Einstein was probing something hidden in the nature of light itself. The photoelectric effect had been observed in 1887 by Heinrich Hertz, who noticed that shining ultraviolet light on a metal plate caused it to emit sparks, electrons. The phenomenon itself wasn't surprising. Metals conduct electricity because their electrons are loosely bound and can be dislodged by incoming energy. But the details were baffling. According to classical wave theory, light is a continuous electromagnetic wave. Increasing the intensity of the light should increase the energy delivered to the metal, and therefore the energy of the ejected electrons. But experiments showed otherwise. The kinetic energy of emitted electrons depended on the frequency of the light, not its intensity. Blue light ejected electrons with high energy. Red light, no matter how intense, could not eject electrons at all. There was a threshold frequency below which nothing happened. Above that threshold, emission occurred instantly, within less than a billionth of a second. Classical wave theory predicted a time delay. The wave should need time to transfer enough energy to free an electron. No such delay was observed. Einstein extended Planck's quantum idea beyond the walls of a blackbody cavity to light itself. Planck had assumed that only the oscillators in the cavity walls emitted and absorbed energy in discrete packets. Einstein proposed something more radical. Light itself is quantized. It travels through space not as a continuous wave, but as a stream of discrete particles, corpuscles of energy, each carrying energy equal to Planck's constant times the light's frequency. When a photon strikes a metal surface, it delivers its energy to a single electron in a single, indivisible quantum event. Part of that energy overcomes the work function, the binding energy holding the electron to the metal. The rest becomes the electron's kinetic energy. This explained everything. High-frequency photons carry more energy and eject electrons with higher speed. Low-frequency photons, even in vast numbers, each carry too little energy to free an electron. Emission is instantaneous because it's a discrete collision, not a gradual accumulation. The energy relationship is exact. Photon energy equals the work function plus the kinetic energy of the ejected electron. Einstein's proposal was staggering. It contradicted a century of evidence that light is a wave, evidence from interference, diffraction, polarization. It challenged Maxwell's electromagnetic theory, the crowning achievement of 19th century physics. Even Planck, when he nominated Einstein for the Prussian Academy of Science in 1913, felt compelled to apologize, suggesting that Einstein may have gone overboard in his speculations with his light quantum hypothesis. Robert Millikan spent years meticulously measuring the photoelectric effect, and in 1916 he confirmed Einstein's equation with extraordinary precision. His data points fell almost perfectly on the straight line Einstein's theory predicted. Yet even after this verification, Millikan refused to accept that photons were real. He called Einstein's hypothesis bold, not to say reckless, a theory that flies in the face of thoroughly established facts of interference. He won the Nobel Prize in 1923 for experimentally verifying a theory he did not believe. It was only in 1923, with Arthur Compton's X-ray scattering experiments demonstrating that photons carry momentum and collide with electrons like billiard balls, that most physicists finally accepted the reality of the photon. The quantum of light received its modern name in 1926 when Gilbert N. Lewis coined the term photon in a letter to Nature. The evidence had become overwhelming. Light is both wave and particle, depending on how you observe it. In 1924, a French aristocrat and theoretical physicist named Louis de Broglie submitted a PhD thesis with an audacious proposal. If light, long understood as waves, could behave as particles, perhaps the reverse was also true. Perhaps matter, electrons, atoms, everything made of particles, could exhibit wave properties. De Broglie proposed that any particle with momentum possesses an associated wavelength, given by Planck's constant divided by the particle's momentum. An electron in motion, by this reasoning, is also a wave. The wavelength is extraordinarily short for macroscopic objects, far too small to detect, but for subatomic particles like electrons, the wave nature should be observable. It was a beautiful symmetry. Light quanta behave like particles. Material particles behave like waves. The universe does not divide neatly into waves and particles. At the quantum scale, everything is both. In his 1924 paper, de Broglie wrote, "We are then inclined to admit that any moving body may be accompanied by a wave, and that it is impossible to disjoin motion of body and propagation of wave." Experimental confirmation came swiftly. In 1927, at Bell Labs, Clinton Davison and Lester Germer fired slow-moving electrons at a crystalline nickel target. The electrons scattered in a pattern characteristic of wave diffraction, exactly the pattern predicted by de Broglie's wavelength formula and consistent with Bragg's law for X-ray diffraction. Electrons, indisputably particles, were interfering with themselves as waves. De Broglie won the Nobel Prize in 1929 for his discovery of the wave nature of electrons. Planck's reluctant quantization, Einstein's reckless photon, de Broglie's matter waves, these were not incremental refinements of classical physics. They were the collapse of an entire worldview and the birth of something fundamentally new. Classical physics assumed continuity, energy, position, momentum. All could vary smoothly, taking any value. Quantum mechanics revealed discreteness at nature's foundation. Energy comes in packets. Electrons occupy discrete orbits. Physical properties are quantized. Classical physics assumed determinism. Given complete information about a system, you could predict its future with certainty. Quantum mechanics introduced intrinsic uncertainty and probability into the fabric of reality. Classical physics drew clear boundaries. Light is a wave. Electrons are particles. Quantum mechanics erased those boundaries. Everything exhibits wave-particle duality. The nature you observe depends on how you look. These revelations transformed physics. Niels Bohr applied quantum ideas to atomic structure in 1913, explaining why hydrogen emits light at precisely 656 nanometers, 486 nanometers, and 434 nanometers in the visible Balmer series. Electrons occupy discrete energy levels. Transitions between levels emit photons whose energy exactly matches the energy difference. This explained atomic spectra, the unique fingerprints of light that each element emits. Classical physics had no explanation for why atoms produced sharp spectral lines rather than a continuous rainbow. Quantum mechanics explained it immediately. The quantum revolution had profound technological consequences. The photoelectric effect, once a laboratory curiosity, became the foundation for solar cells, light sensors, and motion picture soundtracks. When you charge your phone with solar-generated energy or pass through an automatic door triggered by an electric eye, you are using technology that depends directly on Einstein's 1905 photon hypothesis. De Broglie's matter waves enabled electron microscopy, revealing structures far smaller than optical microscopes could resolve. They underpin the behavior of semiconductors and transistors. Quantum mechanics, born from Planck's reluctant quantization, became the foundation for modern electronics, chemistry, materials science, and much of 21st century technology. But perhaps more significant than any application is what quantum mechanics revealed about the nature of reality itself. For centuries, science had been peeling back layers, revealing the hidden mechanisms beneath observable phenomena. Newton showed that the same force governing falling apples governs planetary motion. Maxwell unified electricity, magnetism, and light. The universe seemed comprehensible, strange, perhaps, but governed by laws that made sense within human intuition. Quantum mechanics shattered that comfort. At its foundation, nature operates by rules that defy everyday experience. An electron does not have a definite position until you measure it. A photon travels through both slits in a double-slit experiment simultaneously, interfering with itself until observation forces it to choose. Particles are waves. Waves are particles. Certainty dissolves into probability. Wave-particle duality expresses the inability of classical concepts to fully describe quantum behavior. Nature is indifferent to the names we assign. Some physicists tell their students to think of light and matter as wavicles, entities that are fundamentally neither wave nor particle, but something for which we have no adequate everyday language. Quantum physics called for a new way of thinking. It still does. Despite more than a century of spectacular success, despite quantum mechanics being the most precisely tested and accurately predictive theory in the history of science, the physical origin of quantization remains, in some sense, mysterious. Why is energy discrete? Why does Planck's constant have the value it does? Why does quantization apply to such diverse systems, from blackbody radiation to atomic orbits to the fundamental forces of nature? These questions remain open, not because quantum mechanics is wrong, but because we are still learning what it means. The story that began on December 14, 1900 continues. Every technology that depends on semiconductors, lasers, or quantum sensors is a descendant of Planck's formula. Every measurement that relies on atomic clocks or GPS satellites depends on quantum principles discovered in those early years. Quantum computing, still in its infancy, exploits wave-particle duality and the strange superposition of quantum states to perform calculations impossible for classical machines. The ultraviolet catastrophe was not merely a technical problem in thermodynamics. It was a crack in the edifice of classical physics, and when Planck peered into that crack, he glimpsed a universe operating by rules no one had imagined. Einstein took the glimpse seriously and found photons. De Broglie saw the symmetry and found matter waves. From their work emerged a revolution that redefined our understanding of light, matter, energy, and reality itself. What began as an act of desperation became the foundation of modern physics. Planck's constant, now fixed by international agreement at exactly 6.6607 E15 times 10 to the negative 34 joule-seconds, is woven into the fabric of nature. It governs the emission of light from stars, the chemistry of molecules, the stability of matter, and the quantum fluctuations of the vacuum itself. It is a reminder that beneath the familiar, continuous world of everyday experience lies a deeper reality, discrete, probabilistic, strange, and more wonderful than Newton or Maxwell, or even Planck himself could have imagined. Max Planck never fully reconciled himself to the revolution he started. He was, by nature and training, a man of the classical tradition. Yet when the data demanded it, when logic left no alternative, he introduced the idea that would shatter that tradition forever. Albert Einstein, who spent his childhood mesmerized by invisible forces, saw deeper into the implications and insisted that light itself is quantized, even when the greatest physicists of his generation told him he had gone too far. Louis de Broglie, a French aristocrat with a radical imagination, completed the symmetry and revealed that matter, solid and particle-like as it seems, ripples with waves at scales we cannot see. They were not trying to be revolutionaries. They were trying to understand what the universe was telling them. And what it told them is that reality, at its foundation, does not behave the way our macroscopic intuition suggests. It is quantized. It is probabilistic. It is wave and particle simultaneously, and it is, in every respect, more astonishing than the most imaginative fiction. This is the moment reality broke. Or rather, the moment we discovered that reality had never been what we thought it was. The classical world of continuous flow and deterministic certainty was an illusion, an approximation that works beautifully at human scales, but fails completely when you look closely enough. What lies beneath is a quantum world, strange and beautiful, governed by Planck's constant and the principles born from a desperate act in December 1900. We are still exploring that world. Every experiment, every observation, every technological innovation built on quantum principles is another step into territory that classical physics could never have predicted. And standing at the threshold of that territory, where the smooth certainties of Newton give way to the discrete, shimmering uncertainties of the quantum, we begin to see something profound. That the universe is not only stranger than we imagine, it is stranger than we can imagine. And yet, with patience and rigor and wonder, we are learning to speak its language.